Hello my dear students, welcome back to your favorite and India's most affordable learning platform, Physics Wala. So in the last session, so that is Units and Dimensions lecture 2, we discussed the principle of homogeneity, so which is a very important topic, and we covered various numericals based on that topic. So in continuation to that, in Units and Dimensions, we are going for the lecture number 3 in today's session. So where in lecture number 3 we cover the simple topics, so such as what are significant figures, so and what are the rules for rounding off the numbers, and then the propagation of errors and multiplication and division in the case of error analysis. So I can combinedly call these two as error analysis. So this part is going to be very important, so where the application of this we'll see it in future chapters as well. Okay, so this is very important. So like previous class, so we are going to take again so the number of numericals to understand the concepts and to apply them. Okay, so my simple request is, so just clear your surroundings, so don't get disturbed by anything. So just for the next 1 hour or 1.5 hours, be with me, write the class notes, and at the end, in the last 10 minutes, prepare the short notes. So that's very important. Whatever the total thing that you learned in this today's class, so just make it as a summary, the short notes, right? Chalo. So let's begin with the significant figures. See, so like you will understand the significant figures with the examples. So just let's see the theory first. So significant figures in the measured values of a physical quantity tell the number of digits in which we have confidence, like how many digits we have confidence. So if we give some number, so in how many digits we have confidence, that means like how accurate it is. Okay, so then larger the number of significant figures obtained in a measurement, so greater is the accuracy of the measurements. So if there are more significant figures, let's suppose, so if I asked you to measure something, length of something, so then one student measured so 2 meters, so other students measured 2.10, so other student measured 2.121. so more the number of significant figure, more is the accuracy, right? Chalo. So then, so what are the rules for continuing the number of significant figures in a given measured quantity? So let's see that. So the first, so all non-zero digits are significant. So write point by point. So the first point is all the non-zero digits are significant. So see this example. So 34.7. So 3 is non-zero, 4 is non-zero, and 7 is non-zero. So here we have 3 significant figures. 3 significant figures. So in the next one, very easy. So we have 1, 2, 3, 4. So 4 significant figures. So whereas in this 1, 2, 3, 4, 5, 6 all are non-zero. So significant figures. 6 significant figures. So this is a simple way. All the non-zero digits are significant figure. Clear? So then all closed or trapped zeros between the 2 significant figures are significant. So for example, so if I write 2.01, so I said non-zero digits are significant. So 2 is non-zero and 1 is non-zero. So the first one and the last one are significant. So between 2 significant figures, if there are any digits, they can be considered as a significant. So between 2 and 1 we have 1 0. So that's why we have total significant figures are 3 here. Clear? So similarly in the next one, so 1, 2, see here, 3 is a significant figure, 2 is a significant figure. So in between 3 and 2, so 0 is trapped. So that's why between 2 significant figures, whatever the digit is there, so that's considered as a significant only. So that's why here it is 4 significant figures. Clear? So next, between 1 and 1, so it's going to be 4 significant figures again. The simple answer. So between any 2 significant figures, whatever the digits that are there, even zeros are there, so they can be considered as a significant. So this is a second rule. So next, the third rule, let's go for the next one. all the initial zeros are always insignificant. So leading zeros are initial zeros. So write, so whether it is before decimal or after decimal. So before decimal or after decimal. So try to understand this one. So most of the students get confused while calculating the significant figures when zeros are included. So here see 0.591. So the leading zeros are initial zeros. So the starting one is considered as insignificant. If 0 is there, it's starting with a 0. So that's why we have 1, 2, 3. Only 3 significant figures here. Only 3 significant figures. Okay. So in the next one, see here. So 0.098. 0 initial, insignificant. So 0 after decimal also. So before or after decimal, if it is starting. Okay. So these two zeros are insignificant. So where 9, 8 are significant. So that's why 2 significant figures. Where the next one, so this 0 is insignificant. And after decimal also, so 3 zeros are there, insignificant. So then 7. So only 1 significant figure. Clear this one? Understood? So but if the 0 is there, for example, if I take one more example, if I take 0.709, so 0.709. So how many significant figures are there here? So initial one is insignificant because leading 0 or initial 0. So then 7 is significant, 9 is significant. So between two significant figures always a significant figure lies. So that's why we have 3 significant figures. Clear this part? Understood? Chal. Next. So the next rule, the fourth rule is ending zeros are significant if placed after decimal. Ending zeros are significant if they are placed after decimal. So try to understand this point. See here. So 2.230. 2.230. So where 2 is significant, you know that, and 2 is significant and 3 is significant, and 0 is placed at the end. So end zeros are significant if they are placed after the decimal. After decimal, end zeros are significant. So that's why here total 4 significant figures. Similarly here, so 422. So these are after decimal and these are the end zeros. So that's why 6 significant figures. And then see here, so these 2 zeros are placed after decimal. So that's why here 3 significant figures. These are 3 significant figures. So and then, so try to understand this example. So 20.00. So how can you write this one? So 2 is a significant figure and then 0 is a significant figure, and after decimal the ending zeros are significant. So in 20.00, so let me write this one here. So in 20.00, so you know that after decimal ending zeros are significant. This one is significant and this one is significant, and 2 is also significant. So now the doubt is, so should we consider this 0 as significant or insignificant? The simple rule is, so this is significant and this is significant. So between two significant figures, whatever the digit that lies is always a significant. So that's why here total 4 significant figures we have. Total 4 significant figures. Clear? Understood? So the starting zeros, initial zeros are insignificant, whereas ending zeros are significant if they are placed after the decimal. After the decimal. Clear? Understood? After, not all the zeros after the decimal are significant, because these 3 zeros are after decimal only, but they are not at the end. They are starting. So that's why insignificant here. So but these zeros, see here, these zeros after the decimal, end zeros. So end zeros are significant. So clear? So let's move further. So next one, the next rule. So the ending zeros without decimal are not significant. Ending zeros without decimal. See in 1500. So these two are the end zeros. Are not significant. So these two are not significant. Only we have 2 significant figures. Done. And then so 200. So after there is no decimal. So without decimal the end zeros are insignificant. So one significant figure. So whereas here, so 240, only one significant figure. So here it is only one significant figure. Done this part? Clear? Understood? Chal. So whatever the number you write, so just how many zeros are there? For example, if you write some 10,000 like this, so then it's going to be only one significant figure. Okay. Chalo. So but if I write so 10500, let's suppose, so then this 0 is significant or insignificant? You know that 1 is significant, 5 is significant. So between 1 and 5, so it's going to be 0. So between two significant figures, it's always a significant. So that's why 3 significant figures, because these two are end zeros. Clear? Chalo. So let's move further. So the order of magnitude is always insignificant. So if I write 13,000, so it's going to be 13 into 10 to the power 3. So okay, so where this 10 to the power 3 is there, na? So this is going to be insignificant. So this part is going to be insignificant. So whereas, so these two are significant. So 1 and 3 are significant. So or else you can write, so 1.3 into 10 to the power 4, you write it better this way. So we can write this as 1.3 into 10 to the power 4. So then 10 to the power 4 is insignificant. So and 1.3, so how many significant figures we have? So these are two significant figures. Because pure numbers are not significant, that's why I am writing 1.3. So where two significant figures are there. Clear? Chalo. So pure numbers are constant, have infinite significant figures. So the pure numbers are constants. So here it is R. So this is R. So the pure numbers are constant. Constants have infinite insignificant figures. So which means speed of light. So which is a constant. So it have infinite insignificant figures. And then pure numbers like refractive index, which is a constant. So and then this will have infinite significant figures. Okay. So just remember this rule as well. Done? So let's move further. So let's do some questions so that you will get the idea. So just pause the video and try along with me. So 300. So how many significant figures are there in this? So the ending zeros are insignificant before decimal, right? So before decimal means if there is no decimal term, so the ending zeros are insignificant. So that's why, so only one significant figure. So whereas here, so 3 is significant. After decimal we have 0, 1. So this is also significant. So that's why total 5 significant figures. So what about in this? We have, so after decimal 2 zeros are significant, right? Ending zeros after the decimal are significant. So that's why 3 is also significant. So between two significant figures, whatever the term digits are that lying, they are significant. So that's why total 5 significant figures here also. So what about this one? The initial zeros are insignificant. So whether it's before decimal or after decimal. So but ending zeros are significant. So 1 0 are significant. So the 2 zeros are insignificant. So total 2. So what about here? 1, 2, 3, 4, 5. So 5 significant figures. This 0 is trapped between two significant figures. So that's why it's a significant. And then, so here order is insignificant. So 10 to the power 6 is the order. So which is insignificant. 4.2. So which is only two significant figures. And then, so here the initial zeros before the decimal, after the decimal are insignificant. So these three are insignificant and ending zeros are significant after the decimal. So therefore total 4 significant figures here. So then order is insignificant and 2.10. So after the decimal 0 is placed. So that's why it's a ending 0 after the decimal is significant. So total 3 significant figures here. Then here the ending zeros are significant. So 31.00. So that's why here 4 significant figures. So what about here? So 1, 2, 0. So the ending zeros in a number are insignificant. Only 2 significant figures. So what about here? Order is insignificant. So in 130, so only 1, 3 are significant. So that's why again 2 significant figures. So clear? Understood, guys? So these are the simple ways. So you can take these questions for homework. Let's suppose 0.02310. So the question number 1, and then 0.0041040. So then next, so 0.001072, and then so 6.06 into 10 to the power 6. So then 7200 into 10 to the power 3. So take these questions as a homework and write how many significant figures are there in each one. So write, comment it down. Okay? Chalo. So let's go for the next rule. So the number of significant figures do not change on changing the units. So for example, so 2.5 meters is there. So here, which is equals to 250 centimeters. So in 2.5 meters, how many significant figures are there? So 2, 5. So that means 2 significant figures. So what about in 250 centimeters, which is equals to, so this ending zeros are insignificant. So then this is going to be again 2 significant figures. So that means we can say that the number of significant figures do not change on changing the units. Clear? Simple things. Next. So let's go for the rounding off. So till now whatever we have seen is about significant figures. Hope you guys understood about the significant figures. So now let's go for the rounding off concept. So the simple rule is to how many numbers you are going to round off. So for here, round off to 2 significant figures. Through examples we'll understand this concept. So if you have to round off to 2 significant figures, so what you should do is check the third one, check the third significant digit. So if it is greater than 5, so before term increase it by 1. Okay, so I'll tell by example. See here. So here 2.82. So total how many significant figures are there here? 3 significant figures. So in 3 significant figures, so we have to round off to 2 only. So check the third significant figure. So third significant figure is less than 5. So that's why let's keep the previous one as it is. So that's why it's going to be 2.8 only. So 2.82. So where 2 is less than 5. The third significant figure is less than 5. So then the second significant figure lies as it is. So okay. So then, so the next one 2.87. So so here check the third significant digit. So which is greater than 5. Greater than 5. So that's why it becomes 2.9. So increase the second significant figure by 1. So if the third significant digit is greater than 5. So then see here. So 2.85. So if the third significant figure is 5, write this rule. If third significant figure is 5, so then check next significant figure. Check the next significant figure. So if next significant figure, if next significant figure is non-zero, then so keep it as it is. So then second significant figure do not change. So I'll tell through example so that you'll understand better. So then, so if next significant figure is 0, if next significant figure is 0, so then check second significant figure If it is even, so do not change it. So if it is odd, increase it by 1. If it is odd, increase it by 1. So this is the theory. So just I'll tell through an example. See here. So the third example, you see it. So we have to round off to two significant figures. So here 2.852. So now what we do, we generally check the third significant figure. So but the third significant figure, if it is less than 5, we keep it as it is. Second significant figure, we keep it as it is. So if third significant figure, if it is greater than 5, so then we increase the second significant figure by 1. So 2.8, so it will become 2.9 because 7 is greater than the 5. So now, so the question is, what if the third digit is equals to 5? So here 5 is equals to 5. So then what you should do is go for the next significant figure. So which is fourth significant figure, you should check it. So if the fourth significant figure, if it is non-zero, if it is fourth significant figure is non-zero, so 2 is the non-zero. So then what you do is keep the second significant figure as it is. So then it can be rounded off to, so 2.8 only. 2.8 only. Okay. So I'll take 1, 2 or 3 examples so that you will understand better. This part clear? So then let me check the next one. So 2.85. So third significant figure we have to check. So where the third one is here, 5 again. So here 5 is equals to 5. Then what you should do? Check the next significant figure. So in the next significant figure, 4. 4 is again non-zero. So then keep the second one as it is. So 2.8 itself. So now go for the next one. So 2.850. So here, so the third one is 5. So here also 5 is equals to 5. So then what you should do? So you should go for the next one. So the fourth significant figure, it is 0. If it is non-zero, we do not change the second significant figure. So if the fourth significant figure, the next one after 5, whatever the significant figure is there, if it is 0, so then check the second significant figure. If it is 0, so this is 0. So now check the second significant figure. So if it is even, keep it as it is. So here 8 is even, right? So that's why keep it as it is, 2.8 only. So check the next example, 2.750. So in the 2.750, so the 5 is equals to 5. So check the next one, 0. So then what we should do? So we should go for, if it is 0, so then check the next second significant figure. Second significant figure is odd. So odd, increase it by 1. So that means it becomes 2. As 7 is odd, increase it by 1. Okay, understanding? So if the fourth significant figure is 0 after 5, if the next significant figure is 0, so then check the even odd of the second significant figure. So if the second significant is even, so just keep it as it is. So if it is odd, increase it by 1. When this should be applied? Whenever there is 5 in the third significant figure and 0 in the fourth significant figure. Clear? Chal. So next, so the seventh example, see it here. So 4.351. So 4.3, so the next one is 5. So then check the next one. 1 is a non-zero. So if 1 is non-zero, so then this second significant figure, keep it as it is. So 4.3 itself. Clear? Understood everyone? Chal. So next, let's move further. So then this part is very, very important. So where we are going to see after addition, subtraction and multiplication and division of various measurements. So the final result cannot be more precise than the least precise measurement. So we are adding some significant figures which includes decimals or non-decimals, whatever. Okay. So then, so the final answer, whatever that comes, so in that result will not be more precise than whatever the least precise is there in the given terms. So I'll tell through an example. See here. So result should be in case of addition and subtraction. So result should be rounded off the same number of decimal precisions as are present in the number having least number of decimal places. So first understand this through an example. So we have the example 33.3 and then so 3.11 and then so 0.313. So then 3, 2, so this is 7, so this is 6, so this is 3. So just add them. So we have got 36.723. So now what they are saying, so result should be rounded off the same number of decimal precision as are present in the number having the least number of decimal places. So in all these individual terms, which has the least number of decimals? So 33.3 has 1 decimal. So this has 2. So this has 3. So that's why we have to, so here 1 decimal. So the result should be rounded off to the number having least number of decimal places. So in this, the least number of decimals is 1. So we should round off this to 1. So that's why here 36.7, 36.7 means only 1 decimal place we have to round it off. So which comes out to be, so the 36 point, so 7 after 7 it is 2. So that's why 36.7. Clear? Understood? After 2 means, so that's it. Yeah. Clear this part? So just note this down. I'll go for the next one. Just let me have some water, guys. Next. So let's take one more example. So 3 point, so just add these 3.1421, so 0.241, so then 0.09. So then it comes out to be, so 1, 3, so 8, 9, 17. So this is 2. So this is 3. So which comes out to be 3.2731. 3.2731. So this is the final result. So now check. So here how many decimal places are there? 4 decimal. So here 3 decimal. So here 2 decimal. So now the result should be rounded off to the number having least number of decimal places. So which one has the least number of decimal places? So this one, 2 decimal places. So this also should be rounded off to the 2. So that's why it comes out to be 3 point. So 2 decimals means after 2 check the next one. So what is that answer? So this one is 3. So 3 means 7 remains same because it's not greater than 5. So rounding off concept clear? So it's going to be 3.27. Understood? Done? 3.27 or this one? 4, right? Sorry, my bad. Calculation mistake. So this is 3.4 because 2, 3, 4. So that's why it's 4. See here. 3.4731. So that's why it's rounded off to 2 decimals means again the same 3.47 only. Done? Chalo. Next. So this is in the case of addition and subtraction. In the case of addition and subtraction, the result should be rounded off to the number having the least number of decimal places. Clear? Chalo. So next. So in the case of multiplication and division, so the answer of multiplication and division is rounded off to the same number of significant figures as present in the least precise term. So to the same number of significant figure as present in the least precise term. So what does that mean? See here. So here 142.06 into 0.23. So this answer I already wrote it. So 36.6738. So now this answer should be rounded off to the term so which has the least number of significant figures. So here in this how many significant figures are there? So I can see that 5 significant figures. So in this, so there are only two significant figures because the leading zeros are insignificant. So that's why the answer should be rounded off to, so the answer should be rounded off to two significant figures only. So the one which has the least number of significant figures. In the case of addition and subtraction, to the number having least number of decimals there. Here least number of significant figures. Understand the difference? Okay, chalo. So now, so we have to round off to two significant figures. Two significant figures means, so we can write this as 36.6. So check the third significant digit. So third significant digit is 6. So which is greater than 5. So the third significant digit, which is 6, greater than 5. So then increase the second one. So increase the second one by 1. So which is nothing but 37. 37. Clear? Chalo. So next. So 0.90 by 4.26. 0.90 by 4.26. So this answer I already wrote, 0.21126. So now, so this should be rounded off to how many significant figures? So that's the question. So here how many significant figures are there in 0.90? Leading zeros are insignificant. So that's why here only two significant figures. So but after the decimal, ending zeros are significant. So that's why 2. So here 3 significant figures. So obviously we should round off to, the answer should be rounded off. The answer should be rounded off to two significant figures. So if we have to round off to two significant figure, check the third significant figure. What is the third significant figure here? So 0.211. This is the third significant digit because this is insignificant, right? So that's why it will be rounded off to, so 0.21, because the third significant figure is not greater than 5. So that's why the previous one remains same. So 0.21 is the correct answer. Done, guys? Chal. Let's move further. So now let's go for the error analysis. So however hard we try, so the measured value of a quantity is always somewhat different from its actual value. So this gives birth to the error. So let's suppose you are measuring some dimensions of some object. So one time you measured, you got something. Next time you measured, so again you got some minor difference, not major, so just some minor difference. So again next time you measured, so again you got some other value. So some minor difference will be there, right? So that means, so every time you measure, you are getting some other value. So very close value. So then there is some error. There will be some error. So how do you find that error and what are the types of that error? So the first one is a absolute error. So the absolute error is nothing but the magnitude of the difference between the true value and the measured value. So it's the delta x is the absolute error. So which is, so the delta x of the true value magnitude, you have to take the magnitude of true value minus, so the delta x of the measured value. Measured value. Clear this part? So this magnitude we should take, this is nothing but the absolute error. So where delta x is the absolute error. Done? Chalo. So you'll understand when I take the example, this part. So just this error analysis and significant figures, so rounding off, so all these you should understand by the examples itself. The theory is nothing here. Okay. Chalo. So now let a physical quantity be measured n times. So let the measured values are a1, a2, a3, a4, an. So just let's suppose I asked you to measure the length of this one. So one student measured it to be some 10 centimeters. So another student said 10.1 sir. So the another student said 10.11 sir. So the other student said it's 10.15 sir. So like that we measured some n values. I gave it to some 20 students. So each students reported one value. Okay. So then, so what is the actual length of this? How do we get? So all the 20 students, whatever they gave the values, reported their values. So what I did was I take the average of them. Okay. So that is nothing but AM. So this is, write it as AM means here. The like this. Okay. So the printing mistake is there. The arithmetic mean of these values AM is equals to all the values by the number of values. So 20 students values by 20. Just example I am saying. So usually AM is taken as a true value. So this will become the true value. And then this A1, A2, A3 are the measured values. A1, A2, A3 and till AN. So these are the measured values. These are the measured values. Clear? Understood? So now, next. So absolute errors in the measured values of the quantities. How do we find the absolute error now? So the absolute error is nothing but, so let the absolute error delta A1, which is, so the true value AM minus the measured value. What is the first measured value? A1. So and then the second absolute error delta A2, which is, so the true value, so that is the mean value minus the second student measured value. Okay. So and then, so the third student's error value delta A3 is equals to, so the true value mean minus, so the third student's measured value. So like that. So the nth one delta AN is equals to, so delta AM true value minus, so that student's measured value. That's it. So true value minus measured value, that gives the absolute error. So that's what you should remember. So let me take one question so that you'll understand better. So before question, let's see the mean absolute error as well. So what is the total error? Let's suppose 20 students reported. One student has got 0.1 error. So the other student has got 0.2 error. So the other student has got 0.01 error. One more student has got 0.02 error. So now what is the mean absolute error? So all the 20 students, 20 got 20 errors. So now how do you get the mean absolute error? Just students 1 error, students 2 error till student 20 by number of 20. So this is called the mean absolute error. So delta A is a mean absolute error. Just remember to understand the terms properly. Mean absolute error. So the final result of the measured value is written as, so now what is the final value? So the final value is, so the true value plus, so the absolute mean absolute error. So what is the mean absolute error? Delta A. So that means your value will lie between, so the A is equals to AM plus delta A 2. So AM plus minus delta A bar. So where AM is a mean, AM is a true value. That means, so all the students reported 1 value, right? So I asked you the length of this, right? So one student said 10. So one other student said 10.1. So other student said 10.2. So like that 20 students. So all their values by 20. So whatever that I got, that's a AM. So plus. So what is delta A bar? So it's a mean absolute error. So I calculated one student's error. How I calculated that? So we got the mean AM minus, so students 1 value. So students 1's measured value. So that's a error of the student 1. So then mean minus students 2 measured value. So that's then we get the error of the second. So all the errors, if we take the mean, that's called mean absolute error, delta A. So now our final value will be, so the true value AM plus or minus. So this is plus or minus, guys. So this is plus or minus. So delta A bar, which is nothing, this is a mean absolute error. This is a mean absolute error. Understood? So let me take the question so that you'll understand better way. So then take question is here. So okay, so just see this concept also, then we'll see the question based on all. So then relative error or fraction error. So what does it mean by relative error or fraction error? So it's a mean absolute error. It's a mean absolute error by, so AM, so which is a true value. Mean absolute error by true value. So it's a mean absolute error. So mean value or true value, whatever, it's same. So then if you need the percentage, so just fractional error into, do it 100. So what's a fractional error? So delta A. So this is a mean absolute error, delta A bar by AM. So AM is a true value. So into 100 or mean value we call it. Done? Clear? Chalo. So let's take one question, so then you will understand the complete errors. So see here, see the first question, just pause the video and try along with me. So repeated observation in an experiment gave the values 4.2, 4.4, 4.5, 4.3, 4.6. Calculate. So the mean value. So mean value means AM we are finding first. So AM is nothing but A1 plus A2 plus A3 plus A4. So plus A5. Total how many are there? 5 are there. So that's why 4.2 plus 4.4 plus 4.5 plus 4.3 plus 4.6. So by, so 1, 2, 3, 4, 5. So which is AM. So then what is this value? So just add these. So we get, so 6, 3, 9. So 9, 5, 14, 14 plus 4, 18. So plus 2, 20. So that means 2, 8, 6, 12, 16, 20. So total 22.0. So by 5. So then, so calculate this one. 5 ones are, 5 fours are, and 2 0. So 4.4. So then AM is equals to C. Here also, while adding these significant figures, you should use the rule. In the case of addition and subtraction, we are getting this as 22.0. So 22.0 by 5. So 22.0 by 5 means how many significant figures are there here? So how many decimals are there? So 1 decimal, because we should round it off to the decimals having the least number. So the least number is 1 decimal. So that's why it's 22.5 by 0. So whereas if you calculate this, we will get 4.4. We'll get it as 4.4. So then it should be rounded off to, so the one which is having the least number of significant figures. So which is 4.4. This is the AM. So the mean significant, the mean value. So true value, the first one. So and then what is the next one? Next question. So try along with me. So the second one, it's a absolute errors. So what is absolute error? Let's absolute error of the A1. So the first student. So that is AM. Always magnitude you take. AM minus A1. So what is AM? So mean we got it as 4.4. So minus. So the first student measured value 4.2. So 4.4 minus 4.2. So which is 0.2. Understood this part? And then similarly, you can find the delta A2. So directly I am doing. So delta A2 is 4.4 minus 4.4, 0. So then delta A3, which is equals to 4.4 minus 4.5. You should take the magnitude. That's why it's 0.1. So then delta A4, which is equals to 4.4 minus 4.3. So which is 0.1. So then delta A5, so which is equals to 4.4 minus 4.6. Take the only magnitude. So that's why 0.2. So these are the absolute errors we got. So in the third case, what we required? So it's a mean absolute error. So all the errors, add all the errors by, so the mean absolute error. So the third one, mean absolute error is delta A bar. So which is nothing but, so add all the errors. So 0.2 plus 0 plus 0.1, 0.2 plus 0, so plus 0.1 plus 0.1 plus 0.2. So 0.2, 0.4, this total is 5 kada. So then this is 0.6 by 5. So 0.6 by 5. So this is delta A bar. Clear this part? Chalo. So then we got the mean absolute error. So then how do you get the fractional error? So what's the fractional error formula? So just now we have seen. So the fractional error is delta A bar by AM. So the fractional error, the fourth one, the fractional error is delta A bar by AM. So what is delta A bar? We got 0.6 by 5 by, so what is the AM value? So the AM value we got 4.4. 4.4. So just you do this calculation, 0.6 by 5 into 4.4. So that's it. So then the fifth one, so what's a percentage? Right? So that's the question. So what's a percentage error? So the percentage error is nothing but, So we can write, so the fractional error, so delta A by AM into 100. So then delta A by AM value 0.6 by, so 5 into 10 to the power, so 5 into 4 to the power 4.4 into 100, that's it. So then you do this calculation, you will get the, so the percentage in the error. Clear this part, guys? So any doubt? So just let me know if you guys have any doubts in the comment section. Is this point clear? Is this point clear? Done? So you do this as a calculation, okay? So this as homework. So then calculate this value also. So calculate this value also. Done? Chalo, next. So now, so the propagation of errors while adding and subtracting, how the error propagates. See, so the simple thing is, so delta x is equals to A plus B. So just you write it as, so delta x is equals to delta A plus delta B. So what is this one? So the error in result will be equals to the error in the A plus error in the B. That's it. So whereas while subtracting also it's the same thing. So delta x is equals to, so it's delta A minus delta B. So the errors you have to subtract. So we'll take the question, so then you'll understand in the better way. Okay, clear this part? Sorry, minus. So minus also we should add the errors only. So delta A plus delta B, whether it's addition or subtraction, we should add their errors. Okay, so we'll take the question, you'll understand it better. Just write this down. Chal. So let's move further. So let me take the question. So the initial and final temperature of water recorded by an observer are, so these. So then calculate the rise in temperature. So simple thing, first the rise in temperature. Rise in temperature. So first subtract the true values. So what are the true values? See, these are the errors. 0.2 is error, 0.3 is error. Okay. So first, what is the rise in temperature of true value? So which is 78.3 minus, so 40.6. So what I do is, let me write like this, 78.3. So then 40.6. So if you subtract this one, so we'll get, so 13.6. So which is 7. So then 7, here 7. So this is, so 37.7. So this is a true value. So then what is the error? So how do you get the error? So the change in error, so the delta t is equals to delta t1 plus delta t2. Just add their errors. So what is the error in the first one? 0.2. So and what is the error in the second one? 0.3. So the total, it's going to be 0.5. So that means the rise in temperature. So the rise in temperature, the total rise in temperature will be equals to, so the true value, which is 37.7 plus or minus 0.5. So 37.7 plus or minus 0.5. So is this part clear? Is this part clear, everyone? This is in the case of addition and subtraction. So always you should add the errors. Okay, so true value, whether they asked you to add or subtract, you just do that. They asked us to calculate the rise in temperature. Rise in temperature means final temperature minus initial temperature. So that's what I did. So the rise in temperature, which is equals to final temperature minus initial temperature. Right. So then add the errors. Clear? Sure. So next. So for addition and multiplication we have seen, and for subtraction, sorry, for multiplication and division, for addition and subtraction we have seen how the propagation of error takes place. So now for the multiplication and division, so just do one thing. So here x is equals to a into b. So just consider their powers. Consider their powers. So then delta x by x is equals to, so your power is 1, right? So 1 into delta a by a plus, so b to the power 1. So 1 into delta b by b. That's it. Just follow the procedure. We'll do questions so that you'll understand better. This part is very, very important. So then delta a by a plus delta B by B. So if you need the percentage, so the percentage in the error, so which is going to be simply delta A by A percentage plus delta B by B percentage. That's it. So in the case of division also the same thing. So you just write x is equals to A by B. So we can write this as x is equals to A to the power 1, B to the power 1. So whether it is multiplication or division, just care about the powers. Okay. So then here I can write delta x by x is equals to 1 into delta A by A plus B to the power also 1. So 1, don't write B if it goes up, B to the power minus 1. So that's why I'll write minus 1. No. Okay. So simply write, take that power, whether it's numerator or denominator. So into delta B by B. So if you need the percentage, so you can just write it as delta x by x percentage is equals to delta A by A percentage plus delta B by B percentage. That's it. Understood? So we'll take the question so that you'll understand better. Chalo, so let's move further. So take this question, guys. Try along with me. The length and breadth of a rectangular field are measured. So this way. So calculate the area of the field with proper error limit. So the length is given and breadth is given. So of the rectangular field. So this is a rectangular field whose length is given as, so 4 plus or minus 0.4. So and then whose breadth is given as 2 plus or minus 0.2. So then, so calculate the area of the field. First what you do is L is equals to, so sorry, area, we have got L is A is equals to L into B. So first calculate the true value. What is the true value? So length is 4, breadth is 2. So area 2. So now what is the change in the error? So how do you calculate the error? So the delta A is equals to delta A by A is equals to error we are calculating now, because there is error in the length, there is error in the breadth, so that there comes an error in the area as well. So how do we calculate that error in the area? So delta A by A is equals to here L to the power 1, B to the power 1. So that's why delta L by L plus delta B by B. That's it. So then what is delta L by L? So delta L. So what is the change in the length? 0.4. What is the original length? L is the original length. Original length is 4 plus, so change in the breadth, so which is 0.2 by, so original breadth 2. So that we got 0.1 plus 0.1. This is 0.1, right? So then we can write, so 0.2. So therefore delta A by A is equals to 0.2. But what we need? We need delta A. Delta A is equals to A into 0.2. So what is original area? Original area is 8. So 8 into 0.2. So which comes out to be 1.6. So therefore the final area, so the A final area will be true value 8 plus or minus 1.6. So A final is equals to, so the area final plus delta A plus or minus delta A. So which is nothing but final area is 8 plus or minus 1.6, error final. Clear? Understood the concept, guys? So this way you should proceed. Done? Chalo. So let's go for the next one. So the quantities are raised to same power. So then find the delta x. So very simple question. So x is equals to A to the power P, B to the power Q by C to the power R. So here, so we need delta x. So the delta x by x is equals to, so we can write, so A to the power P. So P into delta A by A plus, so Q into delta B by B plus R into delta C by C. R into delta C by C. Okay. So if they ask you to, if they ask the percentage, so then do this way. So P into delta A by A percentage plus Q into delta B by B percentage. So R into delta C by C percentage. That's it. So just what powers they are raised. So take them as a coefficient and then take the delta by that value. Clear? Chalo. So I'll take few more questions. So these are the previous year questions. So just do this. In an experiment, so the percentage of error calculated in the measurement of a physical quantities A, B, C, D are given. So the percentage error, so that means the delta A by A is given, percentage. So how much? 1%. So then delta B by B is given, so which is 2%, and delta C by C is given 3%, delta D by D is given 4%, okay, respectively. So that maximum percentage of error in the measurement X. So what is the maximum percentage of error, where X is denoted as, so A square B to the power 1 by 2 C to the power 1 by 3 D to the power 3. So simply, how do you find the error now? So you know the procedure. So the delta X by X is equals to percentage we required. So the delta X by X percentage is equals to 2 into delta A by A percentage. A to the power 2, right? So that's why 2 into delta A by A, plus here half into delta B by B percentage, plus next, so 1 by 3 into so delta C by C percentage, and then so delta 4, this is 3, right? So 3 into delta D by D percentage. Clear? So then simply substitute the values. So here 2 into, so the delta A by A is given as 1. So plus 1 by 2 into, so this is given, take 2 delta B by B. So and then 1 by 3 into, so delta C by 3. This is given as 1 by 3. C is a delta C by C. So 1 by 3 into 3. Yes, fine. So this is 3 into, so what is delta D by D? So delta D by D is given as 4, right? 4. So that's it. So now, so this is 2 plus, so 2 cancel 1, plus this is 1. So plus 3, 4, 12. So this is total 16%. So the correct answer is option D, 16%. Okay, clear? So the simple question, that's it. Next. So let's move for the next one. So what's the question says? In the experiment, 4 quantities A, B, C, D are measured with percentage errors. So A, B, C, D percentage errors are given. That means delta A by A percentage is 1, respectively they said. So delta B by B percentage they said, so how much? 2. So delta C by C percentage they said, so 3. So delta D by D percentage they said, so which is 4. So respectively. So quantity P is calculated as follows. So P is given. So this P is equals to A cube B square by C D. Okay. So we need, so the quantity P is calculated. So P percentage we required, the error in the P. So delta P by P percent. Sorry guys. So delta P by P percentage is equals to 3 into delta A by A percent plus 2 into delta B by B percent plus, so C to the power 1. So that's why 1 into delta C by C percent. So again D to the power 1. So 1 into delta D by D percent. So then calculate the values. So 3 into delta A by A, 1. So plus 2 into delta B by B, 2. So plus, so 1 into delta C by C, 3. Plus, so 1 into delta D by D, 4. So this comes out to be 3 plus 4 plus 3 plus 1 into 4. So which is 4. So then this is 7, 10, 14%. So which is option A. Clear? Understood guys? Chalo. So let's go for the next one. So what's the next question says? A student measures a distance traversed in free fall of a body initially at rest. So body is initially at rest. So then in a given time, so he uses this data to estimate g value. So the acceleration due to gravity. So if the maximum percentage in the measurement of the distance and the time are E1 and E2 respectively. So the percentage error in the estimation of G. See, so he said the maximum percentage errors in the measurement of the distance and time are E1 and E2. So see here, so for a freely falling body, what is the time taken? So the time taken by the freely falling body, we know it as root over 2h by g. So he is estimating the value of g, the student, right? So make the g this side, so square it on both sides first. So t square is equals to root over t square is equals to 2h by g. From here g is equals to, so 2h by t square. So now we need the percentage error in the estimation of g. Percentage error in the estimation of g means, so delta g by g percentage we required from this formula. So 2 is however constant, so just keep it aside. So then delta h by h percent plus, so 2 into this one, delta t by t percent we can write. Delta h by h percent, h to the power 1, right? So that's why delta h by h percent plus 2 into delta t by t percent. So what is delta h by h? Delta h by distance. See here, maximum percentage errors in the measurements of the distance. H is nothing but from how much height it is falling. So that's nothing but the distance, right? So it's given as E1 plus 2 times, so delta t by t. So what the time, the maximum percentage error in the time is given as E2. So that's why in the delta t by t place we are writing E2. So that's why the final answer, so in the percentage error, the maximum percentage error in the value of G is equals to E1 plus 2 E2. So the options are also in the terms of E1 and E2. So E1 plus E2 E2 means option B is the correct one. Clear? Chalo, let's move for the next one. So the next question, see here. So if the error in the measure value of a sphere, so if the error in the measurement of radius of the sphere, so radius of the sphere means delta r by r percentage is given, so 2%. So then the error in the determination of volume of the sphere, so consider this is the sphere whose radius is r. So then volume formula will be 4 by 3 pi r cube. So we need the percentage error in the volume. So the delta v by v percentage we required. So however these two are constant, keep them aside. So then r is the variable. So 3 into r to the power 3, right? So 3 into delta r by r percentage. So 3 into, so what is delta r by r is given? So 2. So which is nothing but total. So the volume percentage change, so which is 6%. Done? Chalo, next. So let's move for the next question. So this question says, the density of a cube is measured by measuring its mass and length of its side. So then if the maximum error in the measurement of mass, so the maximum error in the measurement of mass, delta m by m percent, so length, so delta l by l percent, so which is given as 3% and then 2%, fine. So the maximum error in the measurement of density, so they are said the density of the cube is measuring by its mass and length. So density formula is what? Mass by volume, right? So mass is measured in m, so volume in terms of length, so cube volume in terms of length is what? L cube, that's it. So rho is equals to, so I'll write here, so rho is equals to m by L cube, right? So cube's mass by cube volume, volume of cube is L cube. So then, so the percentage error in the density we required, so delta rho by rho percentage is equals to m to the power 1, which is delta m by m percentage plus, so L, so 3 into delta L by L percentage. So in the question they gave delta m by m percentage, so 3 plus, so delta L by L 2, so 3 into 2 6 plus 3 9%. So the correct option is option D. Clear? Chal, next. So next question. Percentage errors in the measurement of mass and speed are given. So the mass delta m by m percentage is given. So how much? 2%. So speed, so delta v by v percentage is given. So 3%. So then the error in the estimation of kinetic energy obtained by measuring the mass and speed. So we need delta KE by KE percentage we required. Right, simple thing. So what's the KE formula? KE, kinetic energy, you already learned in the 9th grade, half mv square. Right. So if you required delta KE by KE percentage, if you required, so half is constant, so m to the power 1, so which is delta m by m. 1 into delta m by m means delta m by m percentage. So here power is 2, so that's why 2 into delta v by v percent. So that's it. So delta m by m, so which is 2 plus, so 2 into delta v by v, 3, so 2 6 plus 2, 8%. So the correct option is A. Clear? So 3 2s are 6 plus 2, 8. Yes. Done? Yes. So next, let's move for the next question. So what's the question says here? A certain body weighs 22.42 grams and has a measured volume 4.7 cc. So the possible error in the mass and volume, so that means delta m by m is given, so which is 0.01 gram, and delta v by v is also given, so 0.1 cc cubic centimeter. So then maximum error in the density. So original mass is given and original volume is given. So then error in the mass is given, error in the volume is given. So then we have to find what is the error in the density. So what's the density formula? Density is equals to mass by volume, right? So from here simply, so what's a delta rho by rho? Percentage, they asked percentage? No. So we have to calculate percentage only. See here, options, it's there in percentage. So then mass is given. So what is mass? So the delta m by m percentage plus, so delta v by v percentage. That's it. So do the calculation, guys. So I'll just have some water. So do this calculation. Faster. So here the delta rho by rho percentage is given as, so delta m. So what is the change in the error? Sorry, this is not the whole thing. My bad. So here delta only percentage error in the measurement of mass. Okay, so delta m is given. So this much error can occur, which means delta m. So and then the volume in the error in the volume is 0.1 cc. Yes, yes, this is correct. So then, so a certain body weighs, so mass is given, so which is 22.42 gram. So and then volume is also given, which is 4.7 cc. So then how can we write this one here? So delta m, which is 0.01 by m. So what is m? 22.42. So into percentage means let's write 100 plus, so delta v by v. So what is delta v? 0.1 by, so then this one v, how much? 4.7 into 100, right? So now, so we get this as, so this is 1 by 22.42. So plus, so this is what, 10 only, right? So 10 by 4.7. So then we can write this as, so this one 1 by, so take the approximation value. So I'm taking it as 1 by 20 plus this is 10 by 5. So which is nothing but 0.05 plus 2. So which is 2.05% approximately. So which is nothing but approximately 2 you can take. Clear, guys? Understood? Chalo. So next. So that's it from my end. So this is all about the error analysis. So the last part, whatever we did after the significant figure, so that's the error analysis. So that is very, very important. Okay. So you just majorly focus on the error analysis where we get the applications of error analysis in most of the chapters, in the upcoming chapters. Okay. So don't just go away. So just write the summary again of the today's session, and then so do practice the questions of previous year. Okay, chalo, we'll meet in the next session. So with the 4th lecture of units and dimensions. So till then, keep studying. All the very best, guys. Bye.